Perhaps you've caught wind of the news. Our solar system is currently playing host to a peculiar and captivating visitor from beyond. Comet 3 I/Atlas exploded into astronomical prominence during the early days of July 2025, when observers of the NASA-funded Atlas Survey telescope, the Asteroid Terrestrial Impact Last Alert System, operating near Rio Hurtado, Chile, first spotted its distinctive signature against the cosmic backdrop. From that pivotal moment forward, researchers worldwide have mobilized an unprecedented effort to capture every available detail about this enigmatic wanderer. The result? An avalanche of publications, urgent bulletins, scientific papers, and yes, more than a few heated debates surrounding the first interstellar object to grace our celestial neighborhood in 6 long years. Yet amid this whirlwind of media attention and scientific fervor, a crucial question emerges. What concrete knowledge have we actually gained? Which claims about this comet stand on solid ground, and which drift into the realm of imaginative speculation? I'm Alex McColgan, and you're watching Astrum. Come along with me as I provide you with an essential update on 3I/Atlas, cutting through the cacophony of conflicting reports to reveal what truly makes this visitor so extraordinary, perfectly timed for its closest approach to the Sun on October 30th. If nothing else demonstrates it, the extraordinary buzz surrounding this comet showcases just how vibrant and rapidly evolving the field of scientific research can be. When I produced my initial video covering 3I/Atlas back in July, researchers had published merely 4 papers mentioning it by name. Fast forward to September when I'm writing this, and that number has exploded to nearly 70 publications. This dramatic increase represents an enormous leap forward in discoveries, confirmations, and enhancements to our collective understanding of this object. Before diving into the most recent findings, however, let me refresh your memory on where our journey left off. In that earlier video, I explored the initial detection of Comet 3I/Atlas, whose designation reflects its position as the third interstellar object documented visiting our solar system, along with the Atlas Survey telescope responsible for its identification. I drew comparisons with the celebrated Oumuamua, which passed through our solar system during 2017, and Borisov, which astronomers discovered in 2019. Unlike its 2 interstellar predecessors, 3I/Atlas appears to be traveling at extraordinary velocity, an astounding 58 kilometers per second, and possesses remarkable age, with calculations suggesting it formed somewhere between 3 and 11 billion years ago. That summary moved quickly, so I strongly encourage you to watch my first video, linked here, for more comprehensive coverage. Since 3I/Atlas made its channel debut, though, we've accumulated significantly more knowledge about it, thanks to innumerable hours of observations and measurements from astronomy facilities spanning the globe. So what fresh insights has this research marathon produced? Given the worldwide attention 3I/Atlas has commanded since its discovery, it has successfully captured the interest of 2 exceptionally prestigious telescopes. Securing observation time with NASA's Hubble Space Telescope presents a notoriously difficult challenge, with researchers required to submit detailed proposals months beforehand to justify every precious minute of telescope access. Fortunately for 3I/Atlas, Hubble maintains dedicated time slots for what astronomers call targets of opportunity, phenomena requiring observation before they slip beyond our reach, granting this unexpected interstellar visitor priority access to skip ahead in the queue. The results proved absolutely worthwhile. Hubble successfully captured this remarkable image of 3I/Atlas on July 21st, when the comet sat 446 million kilometers from Earth. The streaked appearance of background stars conveys a sense of the comet's tremendous velocity, while the teardrop-shaped dust streaming from its icy nucleus creates a striking visual. These observations also enabled Hubble scientists to refine their estimates for 3I/Atlas's nucleus size, placing it somewhere between 440 meters and 5.6 kilometers in diameter. This represents a substantially smaller object than initial projections suggested, since those early size estimates assumed the comet's reflective brightness originated entirely from the nucleus rather than the surrounding coma. Now that the dust is literally cleared, we can examine details with far greater precision, and subsequent observations may narrow these measurements even further. The other major astronomical powerhouse that has turned its attention toward 3I/Atlas is the James Webb Space Telescope. On August 6, Scientists deployed JWST's near-infrared spectrograph in an effort to determine the comet's composition, in research spearheaded by astrochemist Dr. Martin Cordner. Their analysis revealed a complex comet morphology, indicating a variety of different outgassing patterns depending on which elements and compounds were being expelled. It appeared that carbon monoxide and carbon dioxide were sublimating at higher rates during this phase than water, though this balance will likely shift as the comet draws nearer to the sun. While comet tails typically point away from the sun, the research team discovered a surprising quantity of dust emanating from the comet in the sun's direction, caused by dust grains fragmenting as they travel farther from the nucleus, which in turn reflects additional light. This process might be intensified by gas production, as excessive carbon dioxide output could actually be propelling the dust further from the nucleus. Quite dramatic behavior for a feature that appears to us as nothing more than a misty glow. Hubble and James Webb aren't the only NASA telescopes participating in the 3I/Atlas investigation. The Transiting Exoplanet Survey satellite, affectionately known as TESS, has dedicated more than 7 years to conducting an all-skies survey aimed at discovering exoplanets orbiting nearby luminous stars. It employs 4 identical wide-field cameras to map the heavens in 90 by 24-degree strips and has already identified thousands of potential planetary candidates. As it happens, TESS isn't limited to detecting exoplanets. It excels at spotting smaller objects as well. Objects such as comets. In my previous video, I noted that the official discovery of 3I/Atlas was actually preceded by observations dating back to June 14th. However, astronomers working with NASA's TESS mission realized they possessed observational data for this comet extending all the way back to May. The comet appeared in TESS imagery from May 7th through June 2nd, becoming visible in composite deep stack images. With this newly uncovered data, astronomers gained the opportunity to verify earlier measurements of 3I/Atlas and make some fresh discoveries of their own. In a paper published on September 11th, Adina Feinstein, John Noonan, and Daryl Seligman utilized data from TESS to measure 3I/Atlas's brightness. They determined that the average visual magnitude recorded by one of the TESS detectors aligned with previous estimates made by other astronomers using identical data. But the comet was about to defy expectations in yet another way. Between May 7th and June 2nd, the distance separating 3I/Atlas from the TESS spacecraft decreased by 0.9 astronomical units. From this change alone, the authors anticipated the object would grow brighter, since it would be positioned closer to the sun and could reflect more of its light. They calculated that the comet's flux, or the quantity of energy received from it, would increase by a factor of 1.5, corresponding to a magnitude of 20.5. Instead, the object grew dramatically brighter than predicted. Its magnitude jumped to 19.28. This startling surge in brightness resulted from 3I/Atlas increasing its flux by a factor of 5, not 1.5. Observations conducted with the TRAPPIST North and South telescopes reported similar brightness values, confirming no calculation errors had occurred. With such an enormous amount of energy radiating from this object, 3I/Atlas proves far more active than we initially suspected, and may have maintained this activity for an extended period. Combining their magnitude values with the Hubble estimates for nucleus size, the researchers concluded that 3I/Atlas may have already been active when it remained a remarkable 6 astronomical units away from the sun. That's near the outer boundaries of where comets typically begin outgassing, suggesting that 3I/Atlas might have been releasing something more exotic and hypervolatile during this time, such as nitrogen or hydrogen. In my previous video, I mentioned that 3I/Atlas displayed a flatter light curve than Oumuamua, which indicates that it reflects light more uniformly across its surface. Well, Feinstein and her colleagues reached a similar conclusion when they attempted to extract a light curve for this comet using the TESS data. In fact, they encountered such difficulty finding any patterns in the light curve that they couldn't definitively identify the comet's rotation period. They did detect some periodic signals, one occurring every 29 hours and another every 16 hours, but the data contained considerable noise, and TESS may not have possessed sufficient sensitivity to measure this type of parameter for a faint object like 3I/Atlas. Fortunately, Other studies utilizing specialized ground-based telescopes support the 16-hour spin period, so we can feel more confident about the comet's shape and rotational behavior. I've focused exclusively on space telescope discoveries thus far, but telescopes stationed here on Earth have also contributed significant findings about 3I/Atlas. On August 27th, researchers working with the Gemini South Telescope in Chile employed the Gemini multi-object spectrograph to visualize 3I/Atlas in multicolor. Remarkably, the images captured during this session revealed not only the coma surrounding the comet's nucleus, but its tail as well. The tail measured approximately 1/120th of a degree across the sky, which is considerably longer than it appeared in previous images taken using the Gemini North Telescope back in July. This provides additional evidence that 3I/Atlas is growing increasingly active as it approaches perihelion, and suggests exciting developments lie ahead. Who can predict how much more the tail will extend before the comet reaches its closest approach on October 30th? The August session also collected the spectrum for 3I/Atlas. In this recording, you can witness the exact moment when Binyang, assistant professor at Diego Portales University, identified an emission feature in the CN band for the comet, demonstrating that it was releasing cyanide molecules. This occurs when water sublimate upon exposure to sunlight, releasing hydrogen cyanide from the comet, which is subsequently broken apart by sunlight into its component elements. We typically begin observing this phenomenon when a comet reaches between 2.5 and 3 astronomical units from the Sun, which is precisely where 3I/Atlas now finds itself. Other observatories have confirmed this finding, as the once faint CN signature is steadily intensifying over time. A paper published in early September calculated that the comet was releasing 800 sextillion, or 8 times 10 superscript 2 superscript 3, cyanide molecules per second, when it remained just over $3 from the Sun, which actually falls on the lower end of the spectrum for many comets in our solar system. By measuring the ratio of decarbon C2 to cyanide in the coma, the authors classified 3I/Atlas as one of the most carbon chain depleted comets we've encountered. But what exactly does that mean? Carbon chain depletion occurs when a comet's coma or tail lacks longer chain carbon molecules like C2 decarbon or C3 tricarbon. This characteristic is used to classify comets found throughout the solar system and is believed to reflect the conditions under which they originally formed. So, using an upper limit for the comet's C2 production, scientists concluded that 3I/Atlas produces fewer than 0.09 C2 molecules for every CN molecule, and therefore qualifies as carbon chain depleted. Interestingly, Borisov also exhibited this feature, so this may indicate a pattern in the composition of these comets. However, it's crucial to note that the interstellar sample size remains extremely small, so we should exercise caution against overgeneralizing. Regardless, we should maintain close observation of 3I/Atlas as it approaches our Sun. As decarbon production could increase, the comet could begin outgassing more H2O, or something even more dramatic could transpire. As astronomer and comet expert Karamich has stated, these comets are really very fragile, dirty snowballs, and can often fragment. If that happens, we could witness a renewed surge of emissions as the break exposes pristine water ice to the Sun's radiation. In recent days, researchers have analyzed not only how 3I/Atlas emits light, but how it polarizes light. On September 5th, a paper was published by Zuri Gray and colleagues presenting the first ever polarimetric observations of 3I/Atlas, and by extension, only the second ever observations of this kind for an interstellar object, the first being Borisov. Polarimetry is employed specifically to investigate the physical properties of space objects, such as the size of their dust grains, the structure of their surface regolith, and the shape of their coma, in ways that cannot easily be accomplished with other techniques. Gray and her colleagues utilized data from telescopes across Chile, the Canary Islands, and Bulgaria, and managed to discover something about 3I/Atlas that distinguishes it from any other interstellar object, asteroid, or comet we've observed before. They found that 3I/Atlas exhibits an exceptionally deep and narrow negative polarization branch. That might not sound particularly significant, but it means that 3I/Atlas is scattering light in a manner that has never been documented before for any other comet or asteroid in our solar system. This behavior sets it apart from even Borisov, which displayed positive polarization of light, and could position it in a distinct class of small planetary bodies about which we know virtually nothing. To provide some additional context, particles in and around space objects, such as dust or gas, can cause incoming light to scatter in specific directions. This is known as light polarization, and it can be measured by telescopes here on Earth. Experts examine the scattering plane, which is a line formed when looking from the observer to the comet to the sun, and record whether the direction of polarization is perpendicular to the scattering plane, positive, or parallel to the scattering plane, negative. So, the deep and narrow negative polarization of light from 3I/Atlas means that the light is being strongly polarized in a highly localized, parallel direction to the scattering plane. This pattern of polarization is somewhat comparable to some trans-Neptunian objects and centaurs, but additional research is needed to determine exactly why this might be the case. If you believe the newsworthy observations of 3I/Atlas were reserved exclusively for academics, you'd be mistaken. Science truly belongs to everyone, and this next discovery proves exactly why. From September 7th to 8th, portions of the globe were treated to a spectacular lunar eclipse or blood moon as it passed through Earth's shadow. Naturally, this presented an excellent opportunity for amateur astronomers to retrieve their telescopes and observe, but some space enthusiasts weren't focusing solely on the moon. Michael Yeager and Gerald Riemann were photographing the night sky over Namibia when they noticed our friend 3I/Atlas, colored with surprising yet beautiful green hue. Now, this finding hasn't received scientific verification at the time of writing, but comets in our solar system can turn green when they begin releasing diatomic carbon C2, which becomes energized by sunlight and fluoresces near 518 nanometers. This behavior may be typical for other comets in our solar system, but as you'll recall, 3I/Atlas was recently determined to be highly carbon depleted, so it shouldn't really possess much C2 to fluoresce. Perhaps it's a sign that C2 production has accelerated in recent days, but again, we'll require further research to confirm or refute this theory. Whatever the case, it's a stunning image, and this latest mystery has captured the attention of amateur astronomers and scientists alike. At this point in the video, there remains one major area of development in the news surrounding 3I/Atlas that we haven't addressed yet, but it's one I'm certain you've heard about. The name Avi appears frequently in the media coverage of this comet, and he has much to say about where or whom it came from. Avi is a distinguished astrophysicist and Harvard professor who has generated his fair share of controversy throughout his career. His most recent fascination with 3I/Atlas has received mixed reactions from his fellow scientists and the broader public. Back in July, Loeb was already publishing his commentary on the discovery of 3I/Atlas, and initially, it all seemed fairly astrophysical. One of the main points from this paper and from Loeb is that 3I/Atlas is too large to be an asteroid. Early estimates of the comet's radius placed it at around 10 kilometers. Loeb pointed out that this would give the comet a far greater mass than we would have considered possible. Given our current understanding of how much material exists in interstellar space, an object this large entering our solar system should be an exceptionally rare occurrence. In light of this argument, Loeb suggested that 3I/Atlas may be smaller than we originally thought, but he also proposed a controversial alternative, that alien technology could provide the explanation. Just days later, Loeb submitted another paper, along with two collaborators representing nonprofit organizations for interstellar exploration, and the title of this paper is the Interstellar Object 3I/Atlas Alien Technology. While Loeb's first paper only briefly mentioned the idea, this follow-up placed the alien speculation front and center. In it, the authors conducted an analysis of the astrodynamics of the comet, exploring whether it could be technological and possibly hostile. They referenced the dark forest resolution to the Fermi paradox. If you're not familiar, we've covered this in previous videos, but the Fermi paradox poses a question of why we haven't discovered aliens yet, considering the size of the universe and the number of stars that share similarities with our sun. The dark forest idea suggests that perhaps aliens exist out there but are choosing to remain hidden, like prey would hide from a hunter. The authors emphasize that they are exploring this idea for educational purposes, and because it is fun to pursue, irrespective of its likely validity. So, let's examine what they had to say. Firstly, In this paper, Loeb still maintains that 3I/Atlas is too large to be an asteroid. As Loeb and his colleagues should recognize, estimates for any newly discovered object are subject to change, especially as more independent measurements are taken and results undergo peer review. After all, the 10 kilometers value was estimated before we could properly measure 3I/Atlas's coma, and as we now know, that coma is responsible for most of the reflectance we observe. A press release from the Hubble team on August 7 stated that 3I/Atlas measured 5.6 kilometers across at most, but Loeb continues to use the outdated measurements in his alien hypothesis. In a Medium post on August 13th, Loeb directly mentions the Hubble images, but still bases his argument around the older estimates. My point isn't that scientists should be prohibited from pursuing alternative lines of research, but they should at least ensure that the research employs credible data, especially for new discoveries like 3I/Atlas, where the state of our knowledge remains a constant work in progress. As for Loeb's other points, well, they've been challenged by other scientists, particularly in 2 papers by Akam Isnulhak, a geoscientist working at Petronas University in Malaysia. He refutes Loeb's arguments for non-gravitational acceleration to achieve a non-coincidental flyby of Venus, Mars, and Jupiter by referring to the most recent trajectory data for 3I/Atlas, which can be explained far better with natural dynamics than engineer maneuvers. For many of Loeb's critics, this serves as a lesson against jumping to conclusions. As fun as it might be to cry, aliens, we should at least wait for the dust to settle on each new discovery before we start looking for whether it could be a sign of intelligent extraterrestrial life. That way, we'll be far more efficient at coordinating a response if, and when, the evidence truly points to an alien encounter. We've reached the end of our reunion with 3I/Atlas, but as I've demonstrated in this video, this research moves almost as rapidly as the comet itself, so we're by no means finished making new discoveries. On October 30th, the comet will reach perihelion around $1.40 from the Sun, though sadly we won't be able to observe it. At the time this video is released, it will be too close to the Sun to view, but don't panic. It will reemerge by early December, ready for a renewed bout of in-depth analysis. Missions that may be able to observe the comet include NASA's SOHO, SphereX, and MAVEN, not to mention continued observations from Hubble, James Webb, and the Gemini Observatory. So there will be plenty more to come. As 3I/Atlas takes a bow and disappears behind the solar curtain, it leaves plenty of questions for us to ponder. How will its activity change as it reaches perihelion? Will it break apart? How long has it been traveling to get here? And can we trace its elusive origin? It's a race against time to answer these questions. But astronomers are showing no signs of slowing down, and I can't wait to see what they discover next. Solving the mystery of Comet 3I/Atlas is only possible by finding patterns in the data. It requires analyzing mountains of information, spotting subtle patterns, and testing ideas against the evidence. It might seem complex, but it's a skill set anyone could develop with help from today's sponsor, Brilliant. Brilliant is an online learning platform with thousands of interactive lessons in math, science, data analysis, programming, and AI, all created by experts from Stanford, MIT, Microsoft, and Google. It gets you involved from the very beginning, then uses hands-on practice to actively build your understanding. No wonder it's 6 times more effective than passively watching lectures. They've also added a bunch of new courses, like Thinking in Code, or my favorite, Probability and Chance. Each lesson is short, engaging, and designed to make daily learning a habit, so you can reach your goals faster. So, why not give Brilliant a try? Scan my QR code or head to brilliant.org/astrom to get started for free. The link is in the description. You'll also get 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. October 30th arrived with bated breath across the astronomical community. While 3I/Atlas slipped behind the Sun's overwhelming glare, making direct observation impossible from Earth, a constellation of spacecraft positioned throughout the solar system maintained their silent vigil. What they captured would transform our understanding of interstellar visitors forever. NASA's Solar and Heliospheric Observatory, SOHO, stationed at the L1 Lagrange point between Earth and the Sun, caught the first glimpses. The comet had grown substantially, Its tail now stretched an astonishing 2.5 degrees across the sky, nearly 5 times the width of a full moon. But something unexpected was happening. On November 3rd, just 3 days after perihelion, astronomers at the European Southern Observatory detected what they had simultaneously hoped for and dreaded. 3I/Atlas was breaking apart. The fragmentation began subtly. Dr. Elena Rodriguez, leading the observation team at ESO, noticed an asymmetry in the comet's brightness that hadn't been there before. Within hours, that asymmetry resolved into something extraordinary. The nucleus had split into at least 4 distinct fragments, each trailing its own luminous tail of dust and gas. We're watching something that has traveled for possibly billions of years, survived countless encounters with stars and gravitational perturbations, only to meet its end here in our solar system, Dr. Rodriguez noted during an emergency press conference. It's both tragic and incredibly scientifically valuable. The fragmentation unleashed a torrent of previously locked-away material. Pristine ices that had remained frozen since the comet's formation were suddenly exposed to the sun's intense radiation. Spectroscopic analysis revealed something that sent shockwaves through the scientific community: isotopic ratios that didn't match anything we'd seen before. Dr. Kenji Yamamoto at the Tokyo Institute of Technology was among the first to notice the discrepancy. The ratio of deuterium to hydrogen in the newly released water vapor was extraordinarily high, nearly 50% higher than any comet from our solar system, and even higher than Borisov. This tells us something profound about where 3I/Atlas formed, Dr. Yamamoto explained. These isotopic signatures are like fingerprints. They're telling us this comet didn't just form in a different solar system. It formed in a fundamentally different stellar environment, possibly around a star with very different properties than our sun. The implications were staggering. If scientists could determine the exact formation conditions required to produce these isotopic ratios, they might be able to identify the type of star system 3I/Atlas originated from. It was like finding a message in a bottle that had drifted across an ocean, except this ocean was a vast expanse between stars, and the journey had taken eons. But 3I/Atlas had one more surprise in store. On November 8th, amateur astronomer Sarah Chun in Australia captured something that would make headlines worldwide. Using her backyard telescope equipped with a sensitive CCD camera, she recorded a massive outburst from the largest fragment of the comet. In the span of just 6 hours, the fragment brightened by nearly 2 magnitudes, a more than 6-fold increase in brightness. The explosion of activity was so intense that for a brief period, 3I/Atlas became visible to the naked eye for observers in the southern hemisphere, appearing as a faint, ghostly smudge against the pre-dawn sky. I couldn't believe what I was seeing, Chin recounted. I've been photographing comets for 15 years, and I've never witnessed anything like this. The tail was growing in real time. You could literally see it changing over the course of minutes. Professional observatories immediately trained their instruments on the spectacle. What they discovered was extraordinary. The outburst had exposed a pocket of incredibly volatile material, likely nitrogen and carbon monoxide ices, that had been sealed within the comet's interior. As this material explosively sublimated, it created a temporary atmosphere around the fragment that was denser than Mars's atmosphere and rich with complex organic molecules. The James Webb Space Telescope's infrared spectrograph, operating at the limits of its capabilities due to the comet's proximity to the sun, detected over 40 different organic compounds in the expanding cloud. Among them were amino acid precursors, complex hydrocarbons, and most tantalizing of all, molecules that could serve as building blocks for nucleotides, the fundamental components of DNA and RNA. Dr. Maria Santos, an astrobiologist at the European Space Agency, couldn't contain her excitement. We're not saying we found life, but we're seeing the chemical ingredients that could lead to life, preserved from an alien star system. These molecules formed under conditions completely different from our own solar system, yet they're remarkably similar to prebiotic chemistry we believe gave rise to life on Earth. It suggests that the molecular pathway to life might be more universal than we ever imagined. As December arrived, 3I/Atlas, or rather, what remained of it, began its departure from the inner solar system. The 4 main fragments continued to drift apart, each leaving its own distinct trail across space. Astronomers worldwide work frantically to capture as much data as possible before the comet fragments became too faint to observe. The European Space Agency announced an unprecedented collaboration. They would compile all observational data from every major observatory that had studied 3I/Atlas into a comprehensive database, freely available to researchers worldwide. NASA followed suit, committing the Hubble Space Telescope to a final, extended observation campaign in mid-December. By December 15th, the largest fragment of 3I/Atlas emerged from the sun's glare, now receding at 61 kilometers per second. Its velocity slightly increased by its close encounter with our star. The fragment had developed a magnificent tail stretching over 8 million kilometers, clearly visible even through modest amateur telescopes. As astronomers refined their measurements of 3I/Atlas's trajectory, they uncovered one final puzzle that continues to perplex researchers today. Working backward from its current path, calculating the gravitational influences of every star it might have encountered, teams at multiple institutions attempted to trace the comet back to its origin. The results were frustrating and fascinating in equal measure. Unlike Borisov, whose origin could be traced back to a probable source region in the general direction of Cassiopeia, 3I/Atlas's path suggested it had been wandering interstellar space for an extraordinarily long time, possibly hundreds of millions of years, perhaps even a billion. The problem is that stellar motions change over such vast timescales, explained Dr. Robert Kim, an astrodynamics specialist at Caltech. We can trace it back maybe 50 million years with reasonable confidence, but beyond that, the uncertainties multiply. It's like trying to figure out where a particular wave in the ocean originated. After enough time, it becomes mathematically impossible. Some computer models suggested the comet might have originated from a star cluster that has long since dispersed, its sibling stars now scattered across a vast region of the galaxy. Others propose it might have been ejected from a solar system during a close encounter with a passing star, a violent event that would have sent countless comets hurtling into interstellar space. By January 2026, 3I/Atlas had faded beyond the reach of all but the most powerful telescopes. Its 4 fragments, each on slightly different trajectories, would continue their journey through the cosmos, eventually leaving our solar system entirely and returning to the vast darkness between stars. But the data remained, terabytes of observations, thousands of images, hundreds of spectra. Graduate students would write dissertations analyzing this data for years to come. The isotopic measurements would challenge existing models of stellar system formation. The organic molecules detected would fuel new theories about the prevalence of prebiotic chemistry throughout the galaxy. Perhaps most significantly, 3I/Atlas changed how we view our place in the cosmos. For billions of years, countless comets like it have been crisscrossing the galaxy, carry with them samples of the stellar environments where they formed. Some have undoubtedly passed through our solar system undetected. Others will come in the future. Even as 3I/Atlas faded from view, astronomers remained vigilant. Survey telescopes like Atlas continued their nightly patrols of the sky. Somewhere out there, another interstellar visitor is making its way toward us, carrying its own secrets from another corner of the galaxy. When will we detect it? What will it reveal? Will it be a comet like 3I/Atlas and Borisov, or something entirely different? Perhaps a rocky asteroid, or something we've never encountered before? The answers await in the darkness, approaching at speeds we can barely comprehend. And when that next visit arrives, we'll be ready. Our instruments more sensitive, our understanding deeper, our questions more refined than ever before. The story of 3I/Atlas isn't just about one comet's brief passage through our cosmic neighborhood. It's a reminder that we live in a dynamic, interconnected galaxy where the boundaries between stellar systems are permeable. Material, and potentially even life itself, can traverse the seemingly impossible distances between stars. As we watch 3I/Atlas fragment and fade, it left us with more than just data and scientific papers. It left us with a profound sense of wonder and a burning curiosity about what else is out there, traveling through the darkness, waiting to be discovered. The universe, it seems, has many more stories to tell, and we've only just begun to listen. In a laboratory at the Max Planck Institute, a team of researchers is doing something remarkable. Using the detailed spectroscopic data from 3I/Atlas, they're attempting to synthesize molecules matching the exact isotopic composition found in the comet. If successful, humans will hold in their hands, for the first time, matter that matches the chemical signature of an alien star system. It won't be the actual material, of course. That's now millions of kilometers away, racing back into the interstellar void. But it will be the next best thing. A molecular ghost of a visitor that came from somewhere else, stayed briefly, and left us forever changed by the encounter. And perhaps, centuries from now, when humanity has spread beyond Earth and ventures into interstellar space ourselves, we might encounter one of those fragments of 3I/Atlas again, drifting in the cosmic dark, a relic of the time when we were still earthbound, looking up in wonder at visitors from the stars.